Today we're going to be talking about running trains, specifically locomotive to train associations in Kafka Streams. So if you're not too familiar with Kafka Streams, you might be in over your head, but I'll do my best to explain it as easily as possible. My name is Dean Schaefer. I'm a senior software engineer at CSX, graduated from UF with a computer science degree about 7 years ago. The last 4 years, I've been working with Kafka. This is my second presentation, so I'm incredibly excited to be here, but admittedly a little nervous. If you don't know who CSX is or what we do, we are a major Class 1 railroad headquartered in Jacksonville, Florida. And yes, the Jaguars have been incredibly disappointing lately. I think in 2 games, we've had like 5 catastrophic plays on the 2-yard line. So things are going great there. But CSX operates all up and down the East Coast. We cover 26 states, DC, Quebec, and Ontario. Nearly 2/3 of the US population lives in our territory, and most of the goods you use every day travel on a train, so it's really hard to overstate the importance of this logistical network. And like all big old things, airlines, insurance agencies, banks, we've got mainframe programs running COBOL, that is programs that are older than I am. And that's really where enterprise events comes in and the Kafka story. We've got tons of assets and equipment running all over the railroad, nearly 24,000 locomotives, running nearly 250,000 of rail cars, 7,000 crew members across over 1,000 stations and mileposts across the railroad, culminating in 1,600 trains per day. And that's where enterprise events comes in. That's the team I'm the lead senior software engineer on. About 5 years ago, we started this trial run, kind of enterprise architecture's brainchild. They gave us Kafka and kind of told us to go crazy with the charge of democratizing the data throughout the whole kind of company into a Kafka ecosystem. So in the years since, we've created more OpenShift deployments than that, but we've got about 43 stateful sets, kind of your stateful Kafka Stream applications, and then 127 deployments, which are just kind of simple message parsers. All in all, culminating into almost 2.5K partitions, processing 90K records per second. I've got a bit of a data pyramid here, just to kind of give a little bit of scope on the scale of what we do. We've kind of got our source data at the bottom, think GPS pings and data coming from wayside units. We've got reference data in your trip plan or UMLR, which is kind of the stats about your rail cars, how much it weighs, how long it is. Got system data coming from car train management or employees. We aggregate that stuff, and then at the top is kind of what we're talking about today, LTA, or locomotive to train associations. The session description today says a whole lot. I hope I can live up to that. But the goal is a deep dive into kind of the iterative design process of creating our LTA application, how we manage those relationships between locomotives and trains, the different iterations of the applications that we made, and hopefully take a look at some of Kafka's common problems through the lens of our experiences building this locomotive train association process. So we're going to dive into a high-level architecture, just kind of give you a bird's eye view of our ecosystem. We'll talk about the LTA problem, the inputs that go into it, some of the schemas we use. We'll talk through a rough draft of the topology, talk about some of the keying and partition challenges it faces. Some out-of-order events we encountered in that implementation, and then how some of the opportunities that showed, how we handled the edge cases, and kind of wrap things up from there. So Basic architecture overview. We've got railroad events coming from everything, everywhere, all at once, right? 90,000 events per record events per second isn't a small number. We've got your run-of-the-mill XML and JSON, and then we've also got EMP, which stands for Edge Message Protocol, which is a protocol kind of concocted by the Association of American Railroads. It's shared across all railroads. But all those different data formats get consumed in one way or another via microservices, and then written to Kafka topics in protobuffed format. So, what is a train? Raise your hands if you've heard of the kind of joke conspiracy theory, birds aren't real. Yeah. So I'm here to tell you a new one. Trains aren't real, right? They don't exist, man. You probably think we're off the rails. You'd be right. A train is really just a series of railroad cars moved as a unit by one to many locomotives. So it's a concoction. It's a kind of, a train is a group of objects, which makes LTA an authorized group of locomotives traveling together, essentially. That authorization is really the key piece. Think of it sort of as a rental car. You know you have a reservation, and you need some power to move from A to B. Similar to that, you don't really know what you're going to be driving until you show up the day of. So, all in all, the ask is pretty simple. You want to know what locomotives are driving your train that day. To do that, we need to handle establishing associations to trains. We need to end date those associations. And critically, a locomotive should only ever be associated to a single train at a time. So we need to make sure we end prior associations as new ones come in. And why? Why do we want to do all this? Really, a lot of the data at CSX really only gives us one side of the coin. It'll give us the locomotive ID, or it'll give us the train ID. So LTA helps us bridge that gap and helps you tell a more cohesive story. For example, if you have a locomotive speeding down the track where it shouldn't be, you need to know what train that locomotive is assigned to, so you can know what crew members are running that train today, so you can send them a text and tell them to slow down. Similarly, if you want to know where your shipment is, well, it's on a train somewhere. The only way you're going to know where that train is if you can associate the locomotive which is driving it and then collect its GPS pings to explain where the train is. The list goes on, but those are just some of our kind of higher success stories that Enterprise Events has delivered. So, key inputs here, train authorizations, obviously. That's kind of the train itself. It's represented up there as a little license, because trains aren't real. It's really just a train ID, its schedule, its train type, the date it's scheduled to run. It's just an authorization and an intent to run. The second key input is PTC events. That stands for Positive Train Control. It's government regulated kind of incremental initialization of steps you need to take to be able to drive a train. It's that EMP format coming into us. Third is AEI readers. It stands for Automatic Equipment Identification, but essentially think of them as super RFIDs. On the far left, you've got just bricks slapped on the side of every rail car and locomotive, and then it drives by scanners on the side of the railroad, and you get your consist of the whole train in that way. And then last, we've got dispatch events. Dispatch is kind of locked down like a moat because it's a very critical application. So you don't get too much in or out of it, but we do get station arrivals, and we can use that to determine when a train has arrived at its final destination and terminate the train. So the first scheme is here. We've got kind of our LTA proto on the left, and then two state stores, which provide critical perspectives on the right. To start with the LTA proto, we've got our header, which stores your event time, a UUID, sources. You got your local ID, your train UID. I don't know why that text is doing that, but train UID is, again, just train ID, date, etc. Position in train for the locomotive, your association start time and end time. Then we have the TLA state and LTA state. So TLA is train to loco. That's one to many. So you have your train UID and then a list of locos. And then LTA is locomotive to train, and that's one to one. So you have your loco ID, position in train, association start time, as well as your train ID. Both of those states are very important because we need to be able to access them by both of those keys, right? We want to be able to know from the train's perspective which locomotives are all associated to it right now, but also from a locomotive's perspective, if we need to check if there's a active association for this locomotive, we need to be able to look up the latest event for that locomotive. So TLA is keyed by train ID, locomotives keyed by loco ID, provides two different perspectives of the data. So we've kind of set the stage, laid out the architecture, LTA inputs and schemas. Does anybody have any questions right off the bat? Moving on then. So this is actually like the very first rough draft of a topology we wrote up. We've got our LTA and our TLA state there over on the side. We've got train originations at this top row, actually are irrelevant, didn't end up getting used, as well as the kind of interactive queries box X'd out at the bottom there, didn't ever end up being used. So it's important to note that not all of the inputs are created equal. They're all different flavors of data, and they each come with their own unique challenges. To start, we've got train terminations. Those are when the train arrives at its final destination. We want to end date all of the active associations for that train, which is simple enough. The input event comes in, keyed by train ID, it goes in the transform. We can look up all the locos actively associated with the train via the TLA state and emit end-dated associations for all those. Next on the list is 2003s. This is a PTC event, part of that incremental initialization of a train in order to operate on PTC controlled track, which is a lot of it. You need to follow these steps. And 2003 is the train initialization message. It's a conductor on the lead locomotive typing into a little keypad the train ID he's operating that day. So yes, humans are fallible. That data comes in duplicate, mistyped all the time. We have to handle that. But the core of it is it's a locomotive, it's a train ID coming from a locomotive, and that's our first step into establishing an LTA. Right, so just for example, the very first event an engineer types in, there's no pre-existing state for that train. You first want to check in your LTA state store that your locomotive isn't actively associated to another train. If it is, emit an end-dated association for that LTA. Otherwise, we can move forward with establishing the association to the current train. Emitting an LTA. If the engineer goes in and puts that same event in again, we actually want to emit a reaffirming event, a reaffirmation of that association. And well, if he types in a different train ID, we'll want to dissociate from the old train, establish the new train. So you've really got those associations, reaffirmations, and dissociations are kind of the bread and butter of every associating transformer. Locomotive consist is the second step in an incremental initialization. It's a 2032, but it's just a locomotive consist confirmed by the engineer. It's just a list of locomotives. But the first locomotive in the list is the lead loco, which was associated by the 2003. So the 2032s come with a unique challenge of having to look up the established LTA and able to get the train ID associated to the lead locomotive, to be able to rekey it by train ID, to then process it in the transformer and be able to execute within the context of that train state. And last but not least, we've got AEIs, which gives you the entire consist of the train, so you can just pick out the locomotives in it, compare it to the active associations on the train, dissociate any trains that are established in the locomotive state and not in the AEI read, emit reaffirming events for ones that overlap, and establish associations for any locomotives that don't exist in the train's state. So this is obviously a rough draft, but right off the bat, we're going to face some big challenges here, because you can't access state stores by two different keys in the same context from the same transformer, right? Your data has to be copartitioned, which is a little bit of a challenging concept to explain, but I think easy to understand. So I've got a little bit of an example here. But effectively, you need to make sure, in order to appropriately affect your train state, when processing an event for a train, you need to make sure that record is being consumed by the pod which holds that train state. To do this, you need to copartition your data, which requires the keys to be consistent. Your train IDs need to match. You have to have the same number of partitions so that the data is all bucketed evenly. And the same partition hashing strategy just means your keys need to be consistently assigned to those buckets. So to kind of exemplify that here, we've got loco IDs and train keys. The 2003 input topic, we've got this green train key on the circle on the top, and it's being consumed on partition 0. It's being consumed into consumer 0. Since the data is copartitioned, you can always be sure that your train auths and your TLA state for the green train ID will always be on that consumer, but there are no guarantees about loco keys that would be on that pod. So for example, if you tried to look up the pink triangle that's in the green train ID circle, because 2003s are the train initialization, it's loco ID and train ID, but they're coming in keyed by train ID with a loco ID in them. So if you tried to access the locomotive state for that pink triangle, you can see in the bottom the pink triangle is actually being processed into consumer 4. The purple triangles tell a slightly different story. You can see the orange circle would be consumed into consumer 0, and its locomotive ID would also be available in there, but there's no guarantee for that. For example, the blue circle coming in on partition 4 wouldn't successfully find the loco ID in it in the LTA state store because it's being consumed by a different pod. So there's probably 1,000 different ways to fix this problem, but the best way to learn it is to do it. And that's how you end up with something a little like this. Right off the bat, we've included train auths in the topology, which is obviously foundational. It also holds one of the very first challenges we faced when deploying this application, because you'll notice we're using a transformer to just dump that topic into a state store, essentially. And all of our data is coming in with 5 partitions for the most part, running on 5 pods just to keep things simple. But we didn't repartition our train authorization topic. So it had one partition just getting dumped into a train auth store, and then we were like, why are only 20% of our events getting train IDs? This doesn't make sense. Didn't take too long to figure out the data wasn't copartitioned. That's also kind of a cautionary tale for not using transforms to do everything. If you did this through a join, I'm not sure what version of Kafka started doing this, but joins will warn you when you're joining against topics that don't have copartitioned data. Beyond that, the left is mostly the same. We've added the LTA state store to the 2032 Locomotive consist input stream to indicate that you need to look up the train ID associated to the lead locomotive to be able to rekey it by train ID in order to process in the correct context to be able to access the TLA state. The big change here is obviously the right side, where we've really changed the philosophy, or I guess established the philosophy of how these blue transformers are executing. They emit associating events to a repartition topic, kind of intermediate repartition topic, which then gets ingested by this pink transformer, which can check if, by looking up by loco ID into the LTA state store, it can check if this new association is to a different train compared to the last association. So when you emit an association, the pink transformer will check for any prior active associations to a different train. And if it exists, it will emit a dissociation for that locomotive, end dating its relationship to the prior train with the new event's timestamp as the end time. And then it will emit the association to the new train, to the output topic. The idea there is the latest event, the newest association is always last on the topic, so you can join your data kind of consistently that way. But critically here, we've got this kind of feedback repartition topic, because as well as dissociating event, like end dating prior associations, we also need to make sure that we remove that locomotive from the train state. So we can emit that dissociation keyed by train ID back into a repartition topic, which would be consumed by kind of this hijacked eviction request transformer, the purple one, feeding back into the TLA state. And that's job is really just to remove the locomotive from that train state. So you might think this is pretty slick or the dumbest thing ever, but the important part is that it works. Up until you get periods of high consumer group lag. All the repartitioning creates breaks in processing because you're really sending data to different pods at that point, right? So it makes complete sense. And when you have lots of data backed up on your input queues, the Kafka Streams struggles to consume them in the right order. And what ultimately ended up happening was we got 2032s leveraging the wrong 2003 to establish the train ID. So then you'd have your locomotive consist, your 2032s, associating its entire payload to the wrong train. And it's not great. But fortunately, it's only an issue during periods of high consumer group lag, so it's an edge case. But to understand really why that happens, there's two key concepts we need to understand. The first is depth-first processing. We've got a picture of the actual topology that's generated from our stream application up there. So this part's pretty easy to understand. A record moves through the whole subtopology before another is processed. And any data exchanged between subtopology will happen through Kafka, through those repartition topics, which is the break in kind of the subtopologies. So the next important bit is the timestamp flow control. Kafka will do its best job to consume the smallest timestamp when it has multiple records to choose from. So if the large topology at the bottom has a backlog of topics, events on each topic, it will try and consume the smallest timestamp to process next. It's important here to discuss the different types of event time. Right? You have event time, which is the time the actual event occurred. That's what we store in our header time and really what we want to be dealing with. But all of our applications kind of just by default out the gate use ingestion time, which is the time that record was written to the Kafka topic, essentially. So there's an important distinction there. Ideally, they'd be close, but if you have an application down or your AEI read is verified 4 hours late, they obviously get out of order. The other really important bit to that kind of smallest timestamp processing is it's scoped, my understanding at least, is it's scoped to a single topology. So the top are all separate topologies and really have no context of the different input topics. It's not until we repartition everything by train ID, get it in a proper context, that the subtopology is cohesive, and we'll start kind of trying to appropriately consume those repartition topics. So with that, it kind of tells the story, and it's kind of easy to understand why data is getting consumed out of order. So we went through quite a few different ideas on how to solve this. One idea we came up with that we started throwing around was, could we, instead of using repartitioning to access the LTA state, what if we just turned it into a global state store off the output topic? And then we'd be able to freely reference the established LTA at pretty much any point in our processor topology. Kind of reduces the complexity because you don't have to worry about repartitioning so much. And it even enables a sort of precedence check against established LTAs. So if you have an event late coming in, you can check the established Locomotive train association and see its timestamp is newer than the event that's trying to establish a new association. Which you couldn't before because you had repartition steps in between accessing that state. So we're able to add some sanity checks on consuming events. But this really doesn't solve the problem of race conditions between 2003s and 2032s because global tables are updated asynchronously across pods. There's really no guarantee when your pod will get the updates written to the Kafka topic, reflected in its own state store. Ultimately, the solution may be a little heavy-handed, but we came up with kind of a trifecta of a solution. The first being we added a retry mechanism for essentially looking up 2003s for the 2032. You can see this in kind of the retry has some extra arrows around it, and critically, there's a retry, a 2032 retry event state store. So the transformer has an additional state store associated to it, where it can store events to reprocess at a later date if we don't like the conclusions that it came to. So essentially, if your transform process throws a retry exception, it'll get stored in the retry state store with some additional metadata around initial time, retry count. And then you can schedule a punctuator in that transformer to periodically check the state store. And if 10 seconds have elapsed since your last processing of that event, you can try again. If you like the results this time, great, send it on its way, delete it from the retry state store, you're good to go. Otherwise, just increment the retry count and save it off to go again. So the retry mechanism is kind of the critical part of this, but to really take advantage of that, you need to maintain a history of 2003s so that your 2032 has multiple locomotives to reference. If you get 5 2003s in the span of a few seconds because, well, you had a lot of group lag. Your 2032s then need to have the kind of logic to select the appropriate one out of that history, so you can add some time criteria on the 2003 and 2032 joins. This is a great opportunity to call out version state stores introduced in Kafka version 3.5, which really make the whole history pattern here kind of moot because, well, version state stores hold a configurable duration of events and then do the time selection kind of range join for you. It's fantastic. We're getting ready to upgrade all of our applications to take advantage of it. But ultimately, it does resolve just by being a little more stringent on how you join 2003s and 2032s, by giving the retry mechanism, by implementing the retry mechanism, you give streams an opportunity to catch up, process all the events, store them in a history, and then your 2032 can then try again to join against the 2003 it's supposed to. And ultimately, it does kind of solve that problem of locomotive consists getting associated to the wrong train. So, as I said in the keynote this morning, you kind of boil a frog one at a time, and that's how you end up here. You implement something, you see how it works, you make tweaks and adjust it, and kind of go from there. We started with a relatively simple topology, a simple business ask, and then by handling some edge cases, adding a few optimizations in the global state, some additional business asks that came in along the way. For example, we store train terminations in a state store and then filter any incoming events against that state store so that late events won't establish associations to trains that are terminated. But that's how you get here, this kind of monster topology using lots of transforms and states. So yeah, trains have a lot of moving parts. Transforms, punctuation, state stores are all incredibly powerful, but maybe a little too easy to use. It's easy to default to when other operations could be better suited to it. So I encourage everybody to strive to use all the tools available. Don't get yourself pegged into using just one part of the topology. And really, you can avoid a lot of these challenges just by establishing good partitions and keys out the gate. The less you have to repartition your data, the better organized it is out the gate, the easier you'll have, the easier time you'll have processing throughout the whole thing. And that kind of wraps it up. At the end, I've got a little more AI out for you. That's the fellowship of Kafka Streams in a train utopia.